Welcome to the flock. Let's dive into assigning oxidation state number values to different chemicals to determine whether or not a chemical reaction is in fact a redox reaction. Stick around to see how questions like this are answered. What you should already know is that redox reactions always come in tandem. The red always comes with the ox, and the red stands for reduction. In other words, gaining electrons, becoming more negative, or becoming like the cathode, where the cations want to go. And ox part of redox reaction stands for oxidation, i.e. losing electrons, becoming more positive because you're losing something that's intrinsically negative, just like the anode does, and that's where the anions want to go, to the anode. You can remember what each part wants to do according to the mnemonic oil-rig, and that stands for oxidation is losing the oil part. In other words, when a metal becomes mostly oxidized, you have to recharge it because the battery dies. And rig stands for reduction is gaining. And again, the losing and gaining is in terms of electrons. We can thank a dude called Mr. Volta for discovering the electric potential energy unit that we use still to today, the volt. Because he's the first guy that put together this metal separated by a salt bridge, or salt solution, if you will, allowing the electrons to travel from the anode to the cathode. Thanks, Mr. Volta dude, for making my phone possible. If only the stupid battery in this thing would stop being oxidized so quickly. So how can we determine if something is a redox reaction? Well, in order to have redox, one has to get reduced and the other one has to get oxidized. So one has to gain electrons and one has to lose electrons, respectively. So if we were to look at this chemical equation between calcium metal and chlorine gas forming calcium chloride, we would have to take a look at what their charges are before and after. Since calcium is a metal all by itself, we can assume it has a zero charge initially. And chlorine is a diatomic neutral molecule, covalently bonded. It also has a zero charge initially. However, the product of calcium chloride is an ionically bonded species. We know that because it's a metal bound with a nonmetal. And if we look to our periodic table, we can see that calcium has a +2 charge and chlorine has a -1 charge, albeit there are two chlorines present, so technically there are -2 charge overall. So now to determine whether or not this was a redox reaction, we have to compare the reactants to the products. So if we look at calcium on both sides, we see that it went from a zero charge to a +2 charge. In order to become positive, you have to lose something that was negative, i.e. electrons. So in this case, calcium must have lost electrons to become positive. And how many electrons, you might ask? Well, it's a +2 charge, so that means it must have lost 2 electrons. Now let's look to the chlorine. The chlorine is a zero charge on the reactant side and a -1 charge on the product side, but -2 overall. So we know that it gained electrons because it's a negative charge, and electrons are negatively charged species. And how many electrons did it gain? Well, each chlorine atom gained 1 electron for a total of 2 electrons gained. We can now go one step farther and remember our mnemonic oil-rig. We could ask which atom got oxidized and which atom got reduced. So in other words, which one lost electrons and which one gained electrons. We know that the calcium lost electrons, so we could say that calcium got oxidized. And we know that chlorine gained electrons because it became more negative, so we could say that chlorine got reduced. Are you still a little fuzzy about where I got those number values from to put over the top of the chemicals? Well, here's the official charge rules that you can apply to any of the chemicals. These are also known as assigning the oxidation number or the oxidation state. You're going to give a zero charge to any atom that is all by itself. All by myself. In other words, any atom that's in its elemental form will be given a zero charge. This is the reason why I gave the calcium a 0 in the previous example. Also, any diatomic molecule has a zero charge. What are the diatomics? Well, there are 7 of them, and here's a brief list: H2, N2, O2, F2, I2, and Cl2, of course, which is the reason why I gave chlorine a zero charge in the previous example. How about the charges? How do we know where the charges come from? Well, any species that is ionically bonded, or an ionic compound, is going to have a charge associated with it. We know it's an ionic bond if there's a metal paired with a nonmetal. The other time we will assign a charge is when we see hydrogen. Hydrogen is always going to be a +1 oxidation number unless it's bonded to a metal, in which case it will be a -1. And that's it. Those are all the rules you need to remember to assign oxidation states. So let's apply them now. Go ahead and pause the video and see if you can assign the oxidation states for the following chemical reaction. Ready? Go. Let's check your answer. Hopefully you took this one step farther as well and applied the oil rig mnemonic to figure out which one got oxidized and which one got reduced. Let's make sure you have an actual official definition of what a redox reaction is. Basically, any reaction where there is a change in oxidation states. There must be a change in the charges of at least 2 elements from the reactant side to the product side in order for it to be classified as a redox reaction. Let's take a look at a classic example of what a redox reaction is. If we have sodium and chlorine gas reacting to make table salt, NaCl, and we assign the oxidation state numbers, we see that the sodium goes from 0 to +1, that's one of the 2 elements required, and chlorine goes from 0 to -1, so it gained electrons, and that's the other of the 2 elements required. Since there are indeed 2 elements that changed their oxidation state number from reactant to products, we can definitely say that that's a redox reaction. If there is no change in oxidation states from the reactants to the product side, it is not a redox reaction. So here's a classic example of something that is not a redox reaction, which, if you recall from previous videos, it's actually a neutralization reaction because we end up with products of water and a salt when a base and an acid react together. But here, if we compare the reactant side to the product side, we see that Na went from +1 to +1. And O went from -2 to -2. We have 2 H's with a +1 charge. And over on the product side, we also have 2 H's with a +1 charge each. And finally, we see chlorine with -1 and chlorine with -1 from reactant to product side. Since there was no change in any of the oxidation numbers, we know that this is not a redox reaction. Now that we finally have all the definitions and the rules that we need, let's apply it to the question we opened the video with. Is the following a redox reaction? And if so, can we identify which species gets oxidized and which one gets reduced? We know that copper is a metal all on its own. It's lonely.
Yes.
And it's going to have a 0 charge. Oxygen is a diatomic molecule that's covalently bonded, and according to our rules, it will also receive a 0 charge. On the product side, we have copper and oxygen paired together. We have to play a reverse drop and swap, if you will. This is a neutral ionically bound compound because we know that there's a metal and a nonmetal. If we look to our periodic table, we can see that oxygen has a charge of -2 based off of the column it's in. That means that in order for this to be a neutral molecule, copper must have a +2 charge in this case. When we compare the reactant side to the product side, we see copper went from a 0 to a +2. That means it must have lost 2 electrons in order to become positively 2 charged. And oxygen went from 0 charge to -2 charge, which means it must have gained 2 electrons. Since there was a change in oxidation state, we know that this must be a redox reaction. Now, which one got reduced and which one got oxidized? Let's apply our oil rig yet again, and note that the one that lost is the one that got oxidized. So copper, in this case, got oxidized. While oxygen gained electrons, therefore it got reduced. Just as a fun little side note here, we know that the product copper oxide is this blue-green color that we see on pennies. And we also know that the Statue of Liberty has that same blue-green color. That means that it's literally plated with copper oxide on the outside. But what color should the Statue of Liberty be if it wasn't for the redox reaction taking place? Well, it should be the color of copper. like your pennies. So yes, initially, the Statue of Liberty was a bright, shiny, bronze, reddish copper color, but after redox reactions occurred, from it sitting on the salty sea air, we now have the blue-green Statue of Liberty that we're all so familiar with now. Now that we can identify which chemical gets oxidized and which chemical gets reduced, we also want to know which chemical is going to act as the anode and which chemical is going to act as the cathode. If we wanted to build our own battery, this would be useful information to know. We have to give the electrons a happy metal that they want to live on in order for the battery to actually work. The mnemonic you can use to remember which one is going to be the anode and which one is going to be the cathode is as follows. An-ox, 8A, red cat. Honestly, that's a pretty gruesome thing to picture. I mean, can you see this ox like literally consuming this poor little red kitten? Anyways, an-ox is shortened to symbolize anode oxidizes, and red cat is shortened to symbolize reduction cathode. In other words, oxidation happens at the anode, and reduction happens at the cathode. So go ahead and pause the video here and see if you can identify whether this reaction is a redox reaction. If so, why? And then can you also figure out which one gets oxidized, which one gets reduced, and therefore which one is the anode and which one is the cathode? Ready? Go! Let's see if you got it right on this slightly more challenging problem because it involved polyatomic ions. Answer you found as well, where we see that the silver is the one that gained electrons. Notice it's a little bit backwards for this one because it went from a plus charge to a zero charge. In order to go to zero, they had to gain something negative. You had to gain a -1 charge, so 1 minus 1 would give you 0. Whereas copper went from a 0 to a +2 charge, so it must have lost electrons to become more positive. Once we knew that, we could apply the oil rig mnemonic to figure out which one got oxidized and which one got reduced. Then we could use the mnemonic An-ox ate a red cat to figure out which metal would be the cathode, i.e. the silver, and which one would be the anode, in this case, the copper. If we summarize all of the rules we need to apply to identify redox reactions, the first thing we need to do is assign the charges above each individual chemical part or species, using the periodic table. Make sure you're writing those charges above each of the elements respectively and recall the rules, i.e. anything that's diatomic is going to be a 0 charge and any atom that's alone is also going to be a 0 charge. Whereas an ionic species is going to have the charges associated with each element, and you can find those on the periodic table, or from performing a reverse drop and swap. Also keep in mind that hydrogen will be assigned a +1 charge unless it's paired with a metal. Then it would be given a -1 charge. The next thing you need to do is compare the reactant side to the product side to determine whether or not it's a redox reaction. Make sure that there's actually a change in charge from the reactant to the product of at least 2 elements. Then the third thing you need to do is identify which element gets oxidized and which one gets reduced by applying the oil rig mnemonic. From there, you can use the mnemonic An-ox ate a red cat to figure out which one would be the anode and which one would be the cathode. And remember, electrons always flow from anode to cathode. Chickadee check yourself before you wreck yourself and make sure that you can figure out which of these 2 equations is the redox reaction. Make sure you write those charges above each element, compare the reactants to the products, and apply all those rules we just talked about. Once you can identify which one is the redox reaction, explain why, and also figure out which one got oxidized, which one got reduced, and which one would be the anode and which one would be the cathode. Please give this video a giant quacks up, and when you're out of luck in chemistry, subscribe to the duck. Quack you later.
No ducks, no glory.